Hello everyone, my name is Sara Ceccherini and I'm from Aalto University, Finland. I'm here to introduce you to our research entitled Comparing Pulp Reactivity under Direct Dissolution in Copolyethylene 2 case studies. Before to start, I would like to convince you that our research is current and this topic concerns all of us. So, why to study pulp reactivity under dissolution? Maybe some of you are already into this topic, others may not. They may think that this topic does not concern them, but this is not entirely true. Why? We are all part of a population, a global population, which is increasing and increasing. But this is not the only change of the last years. We have seen that our interest in apparel clothing has been increasing over time. We are ready to spend much more money than in the past on this. And these clothes are made of cotton, petroleum-based man-made fibers, and cellulose-based man-made fibers. Now, cotton and petroleum-based man-made fibers are not sustainable for different reasons, but both are not. So there is a gap in this market, and this market is going to be filled by cellulose-based man-made fibers. And here we come because to start producing these man-made fibers based on cellulose, we have first to dissolve cellulose, and this cellulose comes from wood pulp fibers. We have to dissolve wood pulp fibers. Wood pulp fibers are difficult to dissolve because cellulose, their main component, is recalcitrant. Nonetheless, wood pulp can be dissolved. At the end of the dissolution, there is not a proper solution at molecular level. However, there is a colloidal suspension. This colloidal suspension is sufficient for our purpose to produce man-made cellulose fibers. However, different pulps perform differently, and optimal pulps, more reactive pulps, better quality pulps, dissolve in the shortest time as possible and would leave behind the minimum number of particles as possible. Our team has developed a test to assess pulp reactivity, and in particular we focus on the dissolution time. This test is extremely fast compared to other tests which emulate the dissolution process in viscose production, and it is based on a rheological approach. So we have areometer, as you can see here, and this areometer is equipped with a vane and basket geometry. You may not be familiar with this geometry. However, as you can see, there is a cup called the basket, and then there is a vane, a stirrer equipped with 4 flags, orthogonally placed. This setting is necessary because we are working with pulp suspensions and low solids content. In particular, we start with a pulp suspension homogenized at 1.5% solids content. Then we place this suspension into our cup and we further homogenize it into the cup for 5 minutes. Then, without stopping the flow, we inject our solvent. The solvent is the copolyethylene we were talking about. Maybe you are familiar with this solvent because it is used also to assess pulp intrinsic viscosity. Then, without stopping any flow, we start monitoring the dissolution, and this is done tracking torque as a function of time. We start from the injection, and then we see that torque decreases. This decrease is due to the dilution of the system. Then the dissolution properly start, and we see an increase in torque. First, this is linear, then no more linear, as you can see, and finally it stabilizes into a plateau. Once again, we don't have a proper solution at the end. We have a colloidal suspension and we know it, and the test has been optimized in a way to avoid the presence of larger particles. So typically we have less than 10 particles with a diameter above 0.1 microns. At this point, you know that we have practically dissolved the bunch of fibers we had in, and we know that their dissolution time corresponded to the time when the plateau stabilized. This is our test, and we are going to assess our pulps like this. Now that you are familiar with our test, we can move on with our research question. What are the most relevant pulp features that affect pulp dissolution? To answer to this question, we have designed two different case studies. In the first one, we had 4 different prehydrolyzed kraft pulps from different wood species: an eucalyptus, an aspen, a birch, and a softwood mixture. We focused on prehydrolyzed kraft pulps because these are more reactive. They are dissolving pulps, and right now, dissolving pulps are the only pulps that can be used to produce cellulose-based man-made fibers. Well, the issue is that these kind of fibers, these kind of pulps, are more expensive than, for example, paper-grade pulps. For this reason, there is an interest in understanding what makes dissolving pulps so good, so reactive, and what kind of features make them so reactive, and how to boost these features in other kind of pulps, less expensive pulps. For this reason, we had the second case study where we compared the softwood prehydrolyzed kraft pulp with the softwood kraft pulp, paper grade, before and after the treatment. This treatment was a mechanoenzymatic treatment which combined the application of endoglucanase, which depolymerizes cellulose, and a mechanical action due to the friction of the fibers in between the fibers when mixing at high solids content. The solids content was 20%. Let's now compare the different dissolution profiles of the dissolving pulps from different wood species. Here you can see the DTR test profiles. They are easy to read. You have torque, and over time, first it decreases, then it increases at different rates, and finally it stabilizes into plateau. The plateau was clearly different from pulp to pulp, but also the dissolution rate. So in conclusion, each pulp had its own dissolution time, and in particular, the eucalyptus pulp was the best performing, while the softwood one was the worst performing. Now we can compare the dissolution of the prehydrolyzed kraft pulp with that of the kraft pulp before and after the treatment. In the picture, you can see a dashed line that represents the kraft pulp. On the other hand, the solid line represents the prehydrolyzed kraft pulp. You can see how clearly the torque plateau of the kraft pulp was higher than that of the prehydrolyzed kraft pulp, and the dissolution rate, was lower. So, in conclusion, the dissolution time of the kraft pulp measured about 650 seconds, while that of the prehydrolyzed kraft pulp measured only 300 seconds, about. Now, what about the treatment? The treatment had an effect, absolutely, because the torque dropped, as you can see, and the rate increased. So the treatment, this mechanoenzymatic treatment, had a positive effect on our kraft pulp. However, the torque did go down, but not enough to reach the prehydrolyzed kraft pulp. Similarly, the dissolution time improved, but it did not reach the dissolution time of the prehydrolyzed kraft pulp. At this point, this is interesting because we have to understand why. Why did it happen? To understand why the treatment was insufficient to reach the performances of the prehydrolyzed kraft pulp, it was made a full characterization of the pulps. And the results showed only a few parameters had a significant correlation with the dissolution time. These were the molecular mass distribution, the carbohydrates content, the fibrous dimensions, and the intrinsic viscosity. Let's see together how. Before to start discussing about the correlations of the dissolution time, it's worth noticing that the torque plateau increases with the intrinsic viscosity and the molecular weight. And also we know the intrinsic viscosity and the molecular weight are correlated to each other as expressed by the Mark-Howings equation. Here, the correlation between torque plateau and intrinsic viscosity was even linear, and this is also represented by the R square, which measured about 0.97. If the molecular weight and the intrinsic viscosity are important for the torque plateau, they are also important for the dissolution time. Here you see that the dissolution became slower when the molecular weight and the intrinsic viscosity were higher. But now, for a moment, I want you to focus on the orange symbols. The star represents the untreated pulp, the kraft paper grade pulp. The asterisk represents the treated pulp. As you can see, we prove the effect of the endoglucanase, which actually depolymerized the pulp. However, if you focus on the intrinsic viscosity, it is curious that there are these three different pulps in line. One is our treated paper grade pulp, but the other two are the aspen and the eucalyptus dissolving pulps. And we have to remember that the eucalyptus was the best performing pulp. So somehow the treatment had a beneficial effect. But something went wrong, some other properties did not change, and so for this reason the intrinsic viscosity was similar, but the reactivity was different. What? And the answer is that the treatment didn't affect two important properties of the pulps. One is the purity, as you can see on the left, and the other is the fiber cell thickness on the right. So once more, if we are going to compare those pulps which had similar intrinsic viscosity, they are here. They had both different purities, different cellulose percentages, and different cellulose thicknesses. And what about the eucalyptus? That one had the best purity and the thinner cellulose thickness. In conclusion, I'm sure that at least one of you is interested in pulp reactivity. And maybe that person has spent 2 days trying assessing pulp reactivity by simulating the viscous production. I want that person to know that our test takes half an hour for a pre-hydrolysis kraft pulp and, on the other hand, about 1 hour for a bleached kraft pulp. So think about it, give it a chance. And then let's go back to our research question. So what are the pulp features that affect the dissolution time under direct dissolution in cupriethylenediamine? They were the molecular weight distribution, the pulp purity, and the cellulose thickness. So when we aim at targeting better performances, we may improve the pulp purity, we may decrease the fraction of the molecular weight distribution which is associated to longer chains, and then we can work to narrow down the fiber cellulose thickness. At this point, I'm ready for your questions.
So, hello everybody. My name is Luís Alves and I'm working at University of Coimbra, more precisely at the Chemical Process Engineering and Forest Products Research Center. And today I will talk about the influence of different acid anions on the rheology and aggregation behavior of tempo-oxidized cellulose nanofibrils aqueous suspensions. So the objectives of the present work were to change the rheology of tempo-oxidized cellulose nanofibrils, to mold their use as rheology modifiers, and also control the suspension's viscosity and the viscoelastic properties by addition of acids with different anions. We can change the aggregation state. And more importantly, we want to improve the dewatering of negatively charged tempo-oxidized CNFs to produce tempo CNF films in a rapid way. So this work is part of a bigger project, the FilCNF project, which intends to produce films to be used in printed electronics or food packaging, which means substitutes to plastic materials. And we also want to reduce the cost of these films by incorporation of minerals. Minerals are much more cheaper than some nanofibrills due to the production costs of these materials. We also want to improve the water and oxygen barrier properties by incorporation of minerals, increasing the tortuosity of the films. And we also want to keep the transparency of the films the highest possible. So CNFs are really good materials, as we can see, and when studied as isolated fibrils, we can see that present properties even better than diamond or titanium. And even when combined to form a film, some properties are lost, but we still have films with good properties. This was the procedure used to prepare the suspensions of CNF. We started with wood chips from eucalyptus. These chips were subjected to a craft pulping process, followed by bleaching, and the obtained fibers were refined at 4,000 revolutions. Then chemical treatment was applied using sodium hypochlorite in the presence of tempo and sodium bromide. Then we applied a mechanical treatment in the high pressure homogenizer to obtain these suspensions. The suspensions present a consistency of 0.77 and a carboxyl content of about 1.4 millimole per gram. The obtained CNF suspensions were then studied by rheology. Here we have the flow curves of the suspensions at different concentrations, and as expected, the viscosity of the suspensions increases with the concentration. For the lowest concentration, we can see that we are in the diluted region. We do not have the formation of a network. And as we increase the concentration, we can start to have an entangled network. And the strength of this network is increased with the increment of the concentrations. As the stress applied increases, we also can see the shear thinning, which means that we are destroying the network. And finally, we have the fibrils aligned with the flow. So at this final step, we do not have a network anymore. We also can say that the transition from a diluted to a semi-diluted regime for the present work occurs between 0.09 and 0.18%. The same suspensions were also studied by oscillatory tests. Here we have the plot of the phase angle as function of the applied stress. For phase angles higher than 45, the G double prime is higher than G prime, which means that we have a liquid-like behavior. This is the case of the suspension with lower concentration that behaves like a liquid in the entire range studied. For a phase angle of 45, we have a transition, which means that G prime and G double prime present the same magnitude. For phase angles lower than 45, we have solid-like behavior, so G prime is higher than G double prime. And this is the case of the suspension with the highest concentration. The other two suspensions present a transition from solid to liquid as the stress is increased, which means that we have a cross between the G prime and G double prime, and this point is called the yield stress point. Then we changed the pH of the suspensions by adding different acids. Here we have the flow curve of the original suspension at pH 6.9, which is characteristic of a pseudoplastic material. We have the shear thinning, and as we decrease the pH of the suspensions with different acids, we can see that we always have an increase in viscosity. However, if we are using acetic acid, the behavior is quite different compared to the other three. Using the power law model to adjust these four curves at pH 2.3, we can obtain the consistency index, and we can see that this index is very different when we are using acetic acid compared to the other three. An index equal to 1 means that we have a Newtonian fluid, and lower than 1 we are in the presence of a pseudoplastic fluid. So these three suspensions behave close to a Newtonian fluid, contrary to the suspension adjusted with acetic acid, which means that the acetate ions resulted in lower aggregation. Amplitude sweep tests were also used to study the suspensions at different pHs, and as we decrease the pH, the tendency is to increase the apparent yield stress. For the suspensions at pH 6.9 and 4.4, the values are quite similar, with a slight shift to higher values when we are using phosphoric acid. However, if we decrease the pH to 2.3, a large increase in the yield stress is observed. For example, with acetic acid, we have a yield point close to 80 Pascal, which means that the network is more aggregated. And if we are using lactic, citric, or phosphoric acid, the yield point is above 100 Pascal, which means that we are in the presence of a highly aggregated entangled network. Light microscopy was also used to study the suspensions, and as we can see at pH 6.9 we have a clear image, and as we decrease the pH to 2.3 using different acids, we start to have aggregates. These aggregates are more visible in the phosphoric acid suspension, and also the aggregates are larger. These arrows indicate some fibers that are trapped in the aggregates. The results are also confirmed by dynamic light scattering, where we can see an increase in particle size from the suspension with pH 6.9 to the suspensions at pH 2.3, being the sizes obtained for the suspension with phosphoric acid out of the range that can be studied by light scattering. So using dynamic light scattering, we studied the evolution of the particle size with the pH decrease. And as we can see, the tendency is to increase the size as the pH is decreased. However, when we are using phosphoric acid, to pH 2.3 was not possible to measure the particle size because the aggregates are too large and the particles, the size of the particles is out of the range that can be studied by dynamic light scattering. So at pH 6.9 we have particles with size about 106 nanometers, which is expected for individual fibrils. And at pH 2.3, if we are using acetic acid, we have aggregates with a particle size about 400 nanometers. However, if we are using phosphoric acid, we have a highly aggregated suspension, and we cannot measure with this technique. So based on the obtained results, we did our initial trials to prepare films by filtration plus hot pressing. And the films prepared at pH 6.9 were films with 40 grams per square meter, and these films presented good properties. However, the filtration time is quite high. We need 4 hours to prepare the film. Decreasing the pH to 3 with acetic acid, for the same film with 40 grams per square meter, we reduced the time to 1 hour and 40 minutes, keeping the same good properties, which means that when we can speed up the film preparation by 2.4 times. We also did some experiments with phosphoric acid, reducing the pH to 2.3, and using these conditions we can increase the dewatering up to 7 times. However, the films formed are quite brittle, so we need to improve the film formation. So what we can conclude? We can conclude that different anions resulted in very different rheological behavior, and the acetate ions resulted in lower aggregation compared to other ions, mainly compared with phosphate ions. These distinct behaviors can be explained by different interactions of the anions with the virtually neutral fibrils following the off-mass series. We can say that we can control the rheology of the suspensions and improve the dewatering of negatively CNFs using this approach. And to improve the dewatering, phosphate ions are the most effective. The next steps are the preparation of temp CNF films by filtration using different acids and also with CNFs with different carboxylic contents. We need to control the fibrils aggregation to produce films with good properties to avoid, for example, brittle films. And of course, we need to study the effect of the different acids on the mechanical properties and barrier properties. And finally, we need to control the film formation when we are adding minerals at acidic pH to obtain films with improved properties. Finally, I would like to thank to the project team and to FCT and the Portuguese government for the financial support. Obrigado.
Hello, good morning. My name is Álvaro and I belong to University of Beira Interior from the chemistry department and Fiber and Tech research unit. This work, a globulus vessel and fiber analysis with EDX and microfetir, was done under the subvention of Project Impactus with Navigator Company and University of Beira Interior, and also with the participation of Instituto Superior Técnico. The presentation plan is the following. First, I'm going to show the problematics, then the data about vessel quantification and morphological characterization. Point 3, vessel separation method, selection and optimization. Point 4, vessel and fiber chemical characterization. And point 5, main conclusions. This work is based on, and the general project, the intention is to try to minimize or solve two problems related with vessels in printing paper. One is vessel picking, resulting from vessel adhesion or lack of vessel adhesion, and ink refusal due to vessel hydrophobicity. And general strategy is vessel biometric characterization, study of vessel surface chemistry, which we are showing here in this presentation, and separation methods and vessel passivation with chemical or enzymatic treatment, and also analyzing the results in terms of printing properties. In terms of vessel quantification and morphological characterization, first, it was done optical microscopy morphological study of vessels and fibers, and we used also our Morphifiber analyzer for automatic quantification and morphological analysis using image analysis. We initially have done the morphological study and quantification for 3 bleach kraft pulps of Eucalyptus globulus, of acacia and of birch. First point in our study, what we are focusing on Eucalyptus globulus. The fiber numbers were 30 million fibers per gram, and vessel 0.147 million vessels per gram, which gave a fiber vessel proportion of 206 fibers per vessel. We also studied from morph analyzer the vessel's area and fines area, which were 0.32 and 6.6. In terms of microscope, the basic result was 1000 micrometers of fiber length, around 16 micrometers of diameter, and a shape factor of 67.4 for the fibers. For the vessels, average length 300 micrometers, average width 154, which gave micrometers, which gave a shape factor of 1.95, around 2. Here we have more data on morph analyzer. For Eucalyptus globulus, coarseness was 6.1 milligrams per 100 meters. Passing on to the next step, we see, which is our development of a vessel separation method and its optimization. The first step was trying to enrich the suspension with vessels. For chemical analysis, using Bauer magnet, we used for Eucalyptus globulus free screens of 30 mesh, 50 mesh, and 200 mesh. There was a slight increase of fibers, decrease of fiber vessels ratio, which means more vessels in the 50 mesh 50 mesh screen. The same was obtained for acacia and also for birch. But for our purposes, which was chemical analysis, the ones already done and more which are being done and developed, we need more concentration of vessel and a separation of vessel and fibers. We essayed two methods. One is Jacqueline method, which we have the reference of Solzinski and Jacqueline, which is the principle is based on rotation, and rotation creates flocculation, and the vessels are kept outside of the flocks. We have done it by two ways, with a rotor stem and with a agitation impeller. The results are shown here. We see the flocks which are formed and the vessels in the interstice of the fibers, flocks. And then, based on the reference we are going to show onwards, we developed a system based on the breath dynamic drainage jar, consisting of the flow of demineralized water through a 156 micrometer conical hose screen. We can see the result of the separation. We obtained a quite good separation, but we have the problem of still having long fibers associated with the vessels. So we developed the system in two phases, which we had a first phase separating the fibers from the vessel, and the second phase the vessels were passed through the screen and the long fibers retained. In the first step, we used screens of 156 micrometers, conical holes. The intention was to keep the vessels and let the fibers pass. And the second step, we used wider conical holes of 215 micrometers to retain the fibers and let the vessels pass. We can see the results of the separation in these two photos of 40 times ampliation in the microscope, optical microscope. This method of separation has one difficulty, which is it's quite slow. It's quite slow. So we made a scale up with a prototype based on the breach dynamic drainage jar. Even though we had some difficulties obtaining a proper screen. Now we have developed another system using a strainer which can produce in higher quantities the vessels and separated fibers. Now, concerning the vessel and fiber chemical characterization, we did some optical analysis and also EDX, elemental composition, and the results were the following. The main point that we can express and is that the OC ratio for fibers is higher, meaning a higher level of polysaccharides, and which was for OC ratio for globulous fibers was 0.9, and for vessels it was 0.7. I can add the data that the theoretical cellulose ratio is 0.83, lignin 0.33, and extractives 0.11. The results suggest vessels with higher lignin and extractives content. We also have done with Instituto Superior Técnico microfilter surface analysis to detect functional groups. It was done with the support of Professor Bordado, Professora Ana Marques, and Dr. Rui Galhano from Instituto Superior Técnico using Perkin-Elmer microfilter. And there was also the support of a PhD student. The main results are shown here. We can say the spectra obtained from the vessels and fibers are very similar, but there is mainly a difference in the peaks relative to CH bonds and to COC ether group. This can be interpreted in terms of the presence of a higher hydrocarbon concentration, which may be related to the higher hydrophobicity shown by the vessels. Now we have some images of microfilters obtained for vessel for fibers and vessels. And here we have the analysis which was developed in Instituto Superior Técnico. Now I go. So we can sum up the main results. Point 1 is separation methods, which using size exclusion methodology in 2 steps, preceded by fines removal with Bauer magnet. Point 2, the results of ADX, the higher OC ratio observed in vessels, possibly explained by a higher lignin and extractive content. Point 3, it's microsphere results, which can support the previous point, which tells us that spread obtained from vessels and fibers are very similar, but there are differences, significant differences in CH bonds and on the COC ether group. The higher hydrocarbon concentration may be related to higher hydrophobicity shown by the vessels. So I thank you for your attention. We are open for questions. Thank you.
Claro, José.
Hi, hello. No.
Hello.
Buenas tardes, señoras, señores. Good evening. I am Carlos Villar from the INEA. I'm going to moderate the session of raw materials. First of all, congratulations for your excellent presentation. For me, it's almost unknown, but very interesting. And we have now 15 minutes to respond the question of our audience. The first question is for Sara. There are still companies producing dissolving pulp through the sulfite process. Wouldn't it be beneficial to study these pulps, the sulfite pulp?
Well, I can say that we have already started studying these pulps, and of course there is interest because that is the second most in use dissolving pulp, if we think worldwide. But here in Finland, we are mainly focused on these pre-hydrolyzed kraft pulp, and that's why we are mainly targeting these pulps. This doesn't mean that there is no interest in the sulfite pulps because, as we know, like they have different morphological and chemical properties than the pre-hydrolyzed kraft pulp. And actually, it may be interesting to see, to understand why certain properties, for example, swelling, could be enhanced imitating the sulfite pulps. So actually, there is an interest, and we have already tackled this section of pulps.
Thank you, Sara. Now, a question also for Sara. How the solution of CED can correlate with POC reactivity? How the solution in CED correlate with supramolecular structure of cellulose?
Okay, these are also very interesting questions. I would have expected this question about the FOC test because the FOC test is one of the most used tests to assess pulp reactivity for dissolution purposes, especially in the literature. But actually, in our experience, we have preferred comparing our test to another technique, which is the Triber test, which is closer to the Chinese filterability. Also, the Triber test is a filterability method. So we filter, we are simulating here the viscous production, and then we are focusing on the filterability of the dope. And so the amount of particle and the features of the particles that remain undissolved in the dope. what we have seen is that the test is useful, our test with the CED solvent method is useful to correlate, to understand which pulps are much more reactive than the others. So, for example, if we want to make a survey and with different pulps, and these pulps have been produced from different species or from with different pulping conditions, there we can really determine whether a pulp is more or less reactive, and so it will also correlate with the filterability. But if we compare different pulps which are produced in the same day, for example, if we track the quality of the pulps produced within the same day, there it might be challenging to understand the reactivity of these pulps because the reactivity of these is very close, is very similar. So I would say that our test is mainly for understanding what kind of pulps we might be more interested with. And for example, if we modify our pulps by functionalization or other kind of modifications, then we can really see and track in a fast way whether these modifications were useful or not. Yeah.
Thank you, Sara.
You're welcome.
Now a question for Luis. What is the yield of nanofibrillated cellulose from the bleached pulp?
With
Sorry.
the question, so can you repeat, please, the question?
Yes. What is the yield of nanofibrillated cellulose from the bleached pulp?
I don't.
Sorry,
Honestly, I cannot hear the second word. So the idea is why we are using this pulp to produce CNFs, right?
No, the yield, the proportion of nanofibrillated cellulose you obtain from the fibers.
Oh, okay, it's close to 100%. So we can fibrillate basically the total amount. We have something like 95, close to 100% of fibrillation.
Thank you, Luis. And now, also for Luis, what would be the price of such film for packaging compared to existing one? You
Well,
think that
probably it will be quite expensive so far because to produce CNFs we need lots of energy. So we are working on it, and maybe in future we can have good prices. We can be competitive. And the addition of minerals is the purpose of the addition. One of the purposes is to reduce the cost. Of course, we want to keep the properties also in good properties. We cannot lose properties. So we have a balance, and we are working to obtain the best films, but of course with the lowest price possible. But so far, probably are more expensive than the films that are in the market now.
Mm-hmm. The question is how to replace packaging, which is more or less cheap, with such a expensive film.
Yes, we hope that in future we can do it, but of course we need to we have a long way to achieve this probably, because of course the plastic based things are quite cheap and well developed, so we have to improve our films based on bio-based sources like CNF to achieve not only the properties but also the price and the procedures, everything, because in industry everything is made to work with plastic now,
and we have a completely shift to do to work with cellulose bases, for example.
Thank you, Luis. Another for Luis. The film produced at pH 3 with acetic acid is yellowish compared with the other film. Do you see this as a potential issue, as a problem?
Sorry, the film at pH 3 with acetic acid, right?
It's yellowish. It's more yellow compared with the other film. Do you think?
Well,
Do you see this is a potential issue?
no. The final properties of the films produced are quite similar and are quite good. So we want just to improve the dewatering to reduce the time necessary to produce the film. But the properties even can be even improved when we're reducing the pH. For example, if we are, for example, using these highly charged CNFs, we can have an issue with water permeability. So reducing the pH, we can improve the water barrier properties. This is something that we will study in future, but it's our idea that we can improve these barrier properties.
Thank you, Luis. Now a question for Álvaro. With this separation method, would you think it would be plausible to harness separately the fibers for paper making, for example, and vessel from biorefinery biofuels?
Yes, this is one possibility, even though the goal of our works and our strategy right now is to analyze, compare fibers and vessels in chemical terms, and to use strategies to retain the vessels for higher bonding to the paper structure, and to reduce its hydrophobicity with using different possible strategies such as enzymatic treatment and different additives. So that's the initial goal, because we have 2 points. The pulp and paper industry wants to have a high yield in terms of paper production, and if we remove the vessel's current and industrial terms, we would lose a significant amount. There's an economical trade-off here. So yes, it is possible, even though the strategy we are working towards in our project under Pactus, it's to retain and treat the vessels.
Thank you. Another question for Sara. Isn't the presence of hemicellulose supposed to falsely increase pool reactivity? Do you have information of the effect of the concentration of the CED on the reactivity test? I don't know if there is much hemicellulose in your pulps.
Well, we have been studying so many pulps right now that we cover different conditions. We know that the hemicellulose is affecting the dissolution, but not necessarily they consume the reagent in a preferred way, like it happens, for example, in the viscose process. So the effect of hemicelluloses with the CED is different than in the viscose production. On the other hand, we have to consider all the conditions, all the characteristics of the pulps at the same time, because when there is the dissolution,
the fibers dissolve, and fibers are a combination of molecular properties, supramolecular conditions, and morphological conditions. So it's very difficult to understand how each single parameter is affecting the dissolution, and especially when we go wide and we include sulfide and sulfate pulps and paper grade and dissolving pulps. Like, there are so many variables that we have to narrow down our target to understand better what parameters are affecting the reactivity of the pulp. And about the CED concentration, yes, it affects. And our test has been optimized so to get reproducible results, and not only reproducible, but also easy profiles with full dissolution of the pulp. And with full dissolution, I mean that we arrive to have a colloidal suspension, but still, like, we don't have fibers at the very end. So that was the priority, together with the reproducibility of the test. We have an article on this topic, so if people are interested, I can provide if contacted.
Thank you, Sara. I have a curiosity also for you. You have said that the structure of the fiber wall affect the dissolution of cellulose. It would be possible that different bleaching process have effect on this dissolution, cellulose dissolution?
I believe so, yes. I'm positive, because it's not only the bleaching and whatever other pulping condition, because when we do degrade the pulp, it's not only a matter whether the primary cell wall is degraded. We have to go beyond this and also check the secondary cell wall. Whether we are able to narrow down that, then we speed up the dissolution in the later processes.
Thank you, Sara. We have time for another question for Álvaro. How did you remove lignin to obtain pulp for analyze? Álvaro? Álvaro,
Yeah. Yes, I'm sorry. It was, we used bleached kraft pulp, so the lignin was already removed, let's say. The pulp was bleached. Then it was made the analysis, yes, by microsphere in this case.
And another one for Álvaro. It is possible to by micro FTIR to analyze chemical differences in different position of the vessel or fibers? I suppose in
Yes,
position.
yes, microsphere. It takes a small square of, I don't know if it is 10 micrometers, I believe. I'm not a specialist. It was done in Instituto Superior Técnico. And it is possible, even though the difference between fiber and vessels are quite small. It is possible. We are analyzing with other strategies, with sugar content, hemicellulose content, and with HPLC. And we are going to analyze also lignin residuals. So answering directly to the question, it is possible local. That's why we use the microsphere to try to find surface local differences, which are not very significant, but we think it's sufficient to tell some difference between fibers and vessels, which being our intention to find those differences.
I find no more time for more question. Thank you very much. excellent presentation, excellent response. And now the next session will be conducted by Pedro Baptista in the session in this room of energy and environment. Thank you very much.
Thank you.
Thank you.
Bye. Bye. See you.